So good evening all. I'm Pramod Gawal, stay of this course. So I'm going to take a problem solving session 7 on chapter 7 reactor design for multiple reactions. The course tutor is Professor Biswata Mandals, Department of Chemical Engineering, IIT Guwahati. So I think all of you have gone through the week 7 lectures which are available in a SWAM portal. A brief recap, design for the parallel reaction and design for the series reaction. So based on these concepts, I'm going to take some problems, MCQ and numerical ones. Starting from the MCQ one, second order consecutive irreversible reaction where A gives B gives C with their rate constant K1 and K2 carried out in a constant value isothermal batch reactor with a different initial feed composition. The reactor temperature was same in the all the cases. In an experiment where the ratio of concentration B to A initial feed was less than 0.5. The concentration of B increased first, reached a maximum and then declined with the time. However, for all experiment where this concentration ratio was 0.5 or above concentration of B, the concentration of B decreased monotonically with the time right from the beginning. What is the ratio of two read constant K1 and K2? Right. Here is a reaction here given. A gives B and C. So for CB naught by CA okay, is less than 0.5. So here mentioned that the concentration of B increase first. There is a maximum then decline with the times. Here is CB. The initial increase at maximum point then decline. Here initial concentration. Right. And initial rate for right. And slope is positive. And for second case, for CB naught CA naught greater than equal 0.5. They mentioned that the concentration of B decreased monotonically with the time, right from the beginning. CB decreasing. So initial rate since are initial rate and slope is negative. Right. Now rate of B versus CB naught divided by CA naught. Right. So this point is the rate equation with respect to the B K1 CA naught minus K2 Cv naught. There is a B is a reactant. First here first product, that's why here positive. Here is a reactant B, that's the negative. Now Rb not at Cv naught by Ca naught equal to 0.5. Cv naught Ca naught Rb naught. Right. So at this point rate is a 0 equal to K1 Ca naught minus K2 Cv naught. Right. So K1 plus K2 equal to Cv naught by Ca naught equal to 0.5. Right. The option is no. Question 2. The first order series reaction A gives B gives C. It's conducted in a batch reactor. The initial concentration of A, B, and C, given Ca naught, Cb naught, and C naught, respectively, are all non-zero. The variation of Cb with reaction time will not show a maximum. The variation of Cb with reaction time will not show a maximum if here is the condition. Right. So here is a reaction given. So initial rate for A, A1, sorry, minus A, or B, A1 minus K2 minus or C K2 So if K1 C naught is less than K2 C naught, the initial rate of disappearance of A is very small compared to effective rate of formation of the B. So C form monotonically based on the concentration of B in the reactor at any instant of the time. So A gives B is a rate limiting. Right. Therefore, B will be formed very slowly, and as it is formed, it is immediately converted to the C. Therefore, no maximum will be observed. Right here. So T versus concentrations. So is going to reduce C naught C going to form this is initial of CB the rate limiting CB not right. So A is match. So you can check for the other condition also. So K2 will be not greater than K1, K0. Option is. So at this condition, the variation of CV with the reaction time will not show a maximum. Question 3. A second order liquid phase reaction A gives B is carried out in a mixed flow reactor. Here is the second order. Operated in semi-batch mode, no exit streams. The reactant A at concentration CF is fed to the reactor at a volumetric flow rates of F. The volume of reacting mixture is V and density of liquid mixture is a constant. The mass balance for a A. Here you have to mass balance of A mixed flow reactors. Yep. So here mention the second order reactions. So Ra is equal to KCS, yeah, right? So now for mass balance, there is equations rate of accumulation input minus output plus generation minus consumption. Right. Now balance on the A. So d by dt V C A is the volume, C the concentration. Now input F C F, check the unit is a no existence means zero, and here is generation also zero because A is consumed, not a generation. Consumption V by RA means K C A K, right. So meter cube into mole per meter cube, mole per second. So d by dt VCA to FCAF minus VKCA square. So check the options. Yep. So option C and almost same says should be the positive. Option D is correct. So moving to the question number 4. The following liquid phase reaction are carried out in a PFR. A plus C gives twice B plus P with rate equations. Rp is equal to K1 into Ca into CaC. A gives D with rate equation Rd equal to Q2C. What is the ratio of moles of P formed to moles of D formed at a reactor exists if the conversion of C is 50%. No product is present in the feed. So data given, so we have to calculate the ratio of moles P formed to moles D. Data given, initial concentration given 2 kilomole per meter cube and K1 given 1 meter cube per kilomole per second and K2 1 second. So PFR. Right. So XC given 0.5 and this is PFR. So CC means concentration of CAT exists equal to CC naught 1 minus XC, right? So CC means initial given CC naught equal to 2 mole and XC given 0.5. 1. So it's 1 kilomole per meter cube. Right. Now it's equation 1, equation 2. Now I divide equation 1 by 2. So RP by RD, right, equal to K1 CA CC K2 CA. Right. So K1 by K2 equal to CC. Right. So here K1 and K2 given. Right. It's a NCC calculated 1. So P and D will be the equimolar ratio at the reactor exist. Equimolar ratio at the reactor exists. Right. Now question 5. The following gas phase reaction is taking place in a plug-through reactor. A plus 1 by 2 B gives C. A stoichiometric picture of A and B at 300 Kelvin is fed to the reactors. At a 1 meter long length of reactor, the temperature is 360 Kelvin. The pressure drop is negligible. Right. An ideal gas behavior can be assumed. So identify the correct expression relating the concentration of A at a inlet Ca naught, concentration of A at 1 meter Ca and corresponding conversion of AX. Right. So Ca is a concentration of A at any point in the reactor. So Ca is equal to Na. Here is a gas phase reaction. So Na is equal to Na naught 1 minus Xa. V is equal to V naught 1 plus epsilon A Xa. Right. To calculate the epsilon A, so V Xa equal to 1 plus V Xa equal to 0. So it means after conversion and before conversion. divided by V is equal to 0. Right. So here equation given A plus half B gives C. So that ideal condition. So volume percent equal to the mole percent. So equal to 1 1 minus 1.5 divided by 1 1.5 1 it's minus 1 by 3, right? Now V is equal to V naught 1 plus epsilon A to Xa equal to V naught 300 Kelvin T by T naught to T naught by P and 1 plus epsilon A, right? So V is equal to V naught 360 300 1 minus 0.33 Xa. So V is equal to V naught 1.2 to 1 minus 0.38 x. Right. Now put this value in these equations. Right. So Ca is equal to Na V to Na not 1 minus Xa, then V not 1 by 2 1 minus 0.33 Xa. Right. So Ca is equal to 0.83 C naught 1 minus Xa 1 minus 0.33 Xa. Right. Now check the option. The option C is match. Now question number 6. The rate of liquid phase reversible reaction. Egg. Here is a reversible reaction. Egg use twice B. In a kilomole per meter cube per minute at 298 Kelvin is with the rate equations are equal to pi into Ca minus 0.01 Cb, where the concentration Ca and Cb are expressed in kilomole per meter cube. What is the maximum limiting conversion of A achievable in a isothermal CSTR at 298 Kelvin, assuming where A is fed at the inlet. Right here is a reaction given and the rate equation given. So we have to calculate the convergence. Right. So here is a rate equation 0.02 Ca minus 0.01 Cb. So here is a rate of reaction for the rate equation for the forward reaction, and this is for the backward reactions. So maximum limiting conversion of A is achieved at a equilibrium when the forward reaction and backward reaction are equal. So 0.02 CA equal to 0.01 CV with superscript equilibrium. Equilibrium. Now this is initial at equilibrium. So here are species A and B. So initially 1 mole, right? Here is a pure A, pure P, B0 at equilibrium 1 minus Xe. Here is a twice Xe. Based on the stoichiometric. Now this is a liquid phase, so volume is constant. So Ca E equal to 1 minus X AE by V. Here is a V due to the rate, the unit of the rate, and CV equal to CBE equal to twice XAE by V. Now put this value in this equation once, 0.01 minus XAE equal to 0.01 twice XAE by V, right? So XAE 1 minus XAE, so X equal to 1, so XAE 2 by 2. So option C is, so the 50% conversion of A achievable in isothermal CSTR. Now question number 7, an isothermal steady state mixed flow reactor CSTR of 1 meter cube volume is used to carry out a first order liquid phase reaction A gives products. Phase speed at a volumetric flow rate Q containing reactant A at a concentration say A naught mixed with recycled stream at a volumetric flow rate RQ as shown in figure below. So here is the initial concentration, final and flow rate given. So it is observed that when the recycle ratio are 0.5, the exit conversion XAF is equal to 50%. When the recycle ratio is increased to R equal to 2, the new exit conversion in percent will be. A CSTR has assumed to have infinite internal recycling, and conversion of the reactant in CSTR is calculated based on this assumption. So any amount of external recycling does not have any effect on the conversion of CSTRs, whether R equal to 0, R is equal to 0.5, or R equal to 2, or R equal to infinity, right? So XAF will be remain same. That is XAF equal to 50%. So any amount of external recycling does not have any effect on the conversion of the CSTRs. Question number 8. An isothermal aqueous phase reversible reaction P gives R is to be carried out and R gives to P. Is to be carried out in a mixed flow reactors. The reactor rate in kilomole per meter cube per hour is given by R equal to 0.5 Cp minus 0.125 Cr. A stream containing only P enters the reactor and the resident times required in hours for the 40% conversion of P each. So here is a CSTR here. So for us, the performance equation for the CSTR tau equal to P by F plus Cp xp minus Rp, right? So this is a liquid phase. So epsilon P equal to 0. So Cp equal to Cp naught minus xp. So xp given by this is a xp 40%. So Cp is equal to 0.6 Cp naught, right? And Cr equal to Cp naught into xp, right? Equal to 0.4 Cp naught. Right. Now this is equation 1. It's right. So put this value in this equation once. So minus Rp equal to 0.5 0.5 Cp naught 0.6 minus 0.125 to 0.4 Cp naught. So Rp equal to 0.25 Cp naught. Now put this value in these equations. Now tau is equal to V by A equal to Cp naught into 0.0 1 by Cp naught to 0.25, right? So 1.64. So resident time is 1.6. Option C is correct. Now question number 9 and 10. So here is a statement for question number 9 and 10. A simple chemical reaction A gives B is carried out in two CSTRs connected in series. The volume of first reactor is 1.5 times that of second reactors. So V1 equal to 1.5 V2, right? And the temperature of reactor are such that the rate constant of first reactor is 1.5 times the rate constant in the second order. Means K1 equal to 1.5 K2. So the question is that a given above the consistent for a first order reaction kinetics justified? Here is a initial moles given the H reactors and outlet concentration given. So assume right. So assume the first order kinetics. So the performance equation for the first order K tau equal to XA divided by 1 minus XA, right? And XA equal to CA naught minus CA divided by CA naught, right? So now CSTR 1, so XA1 equal to 3.3 minus 1.65 divided by 1.65, right? So 0.5. So here x equal to 0.5, and so for CSTR2, so XA2 equal to 0.25. So XA2 equal to 0.25, right? Now, so, so we can write down K1 equal to V by Fa not equal to XA1 minus XA. Here. So XA1 equal to 0.5 into the 1, right? So K1 V1 divided by Ep naught equal to 1, equation 2. And for the CSTR2, K2 V2 by Ep equal to 1 by 3, 0.33, equation 2, right? Now comparing equation on 1 and 2, K1 into V1 divided by K2 V2 get cancelled. So here is a 3. Now to check the consistency based on the given V1 equal to 1.5 V2 and K1 equal to 1.5 K2, right? So K1 V1 by K2 V2 equal to 2.25. So this is a not consistent, not consistent. So the data given above is not consistent for the first order kinetics. Now second statement, second 10 question number 10, is the data given above consistent for the second order kinetics? So justify. So for second order reaction, so the performance equation K tau A naught equal to XA1 minus XA, yeah, right? So for CSTR, here is CSTR1 and CSTR2, right? So K1, right? V1 by Fa naught equal to XA1 minus Xn. So here is a x7 equal to zero point 0.5 calculated and a2 is equal to 0.25, right? So K1 V1 if we not 1, what is the initial cost? Okay, there is a initial concern 3.3 mole. So x1 is C into 1 minus xx. Okay, right. For CSTR, so sorry, K1 V1 equal to AP0 equal to 0.6 1. For CSTR2, K2 V2 AP0 equal to 0.2693. Question 2. Right. So now based on the equation on 1, 2, so K1 V1 divided by K2 V2 equal to 0.60 divided by 0.2693. So 2.2. And according to the problem statement, so K1 by V1 by K2 V2 equal to 2.2. Right. Almost equal. So this is the consistence. So above data given the data given above the consistent are the second order kinetics. Now question number 11. The CSTR PFR of PFR of equal value are connected in series as shown in below to carry out the first order isothermal liquid phase reaction. A gives P. Here is a schematic. The rate constant is 0.2 per second. The space times is 5 seconds for the both the reactors. The overall fractional conversion of A is rounded up the third decimal place. So here is the first order reaction. So volume is same. So V CSTR equal to V PFR and space time tau CSTR equal to tau PFR equal to 5 seconds. Right. So first here is a first order reaction. The performance equation for the CSTR K tau equal to C naught minus CA divided by CI, right? So here is a K given 0.2 and tau 5. So C naught minus 1. It's CA naught divided by CI right here is also equal to 2. This is equation 1. Now the performance equation for the PFR for first order reaction K tau equal to ln CAI by CAF, right? So put the value K and tau here, so you will get CAI minus CAF equal to 1, right? Equation 2. Now equation 1 and 2, CA not CAI into CAI divided by CAF, right? Into twice into E. CAI get cancels. So CA not CAF equal to twice into E, right? So for convergence, XAA is equal to 1 minus XAF by C naught, right? We can write down this one CF by CA not equal to 1 by C. So here 1 minus 1 by twice, so equal to 0.816 means 81.6%. The overall fraction conversion is 81.6%. Question number 12. The following liquid phase reaction is taking place in isothermal batch reactors. So A gives B and C. So this is the first order and zero order. Second is the zero order. The feed concentration of mole per liters. The time at which the concentration of B will reach its maximum value is given by. So here is a reaction given. So first is the first order. B2C is the zero orders. So write down. So first we write down the rate equations. dCA by dt equal to minus K1 CA, right? This is for this one first order. For this term, for this reaction, dCB by dt equal to K1 CA minus K2 due to the zero orders. So integrate these ones. So here CA not 1 mole per liter given. So you will get CA is equal to E minus K1 T, right? So put this value C is equal to in these equations. So dC by dt equal to K1 E raised to the power minus K1 T minus K2. So here for CB max, maximum CB, dC by dt equal to 0. For so this is going to 0. Okay. So 0 equal to K1 e raised to the power minus K1 T minus K2. So T is equal to 1 by K1 ln K1 by K2. Check the option. Option A is match. Question number 13. So based on the previous statements, The time at which the concentration B will become a zero is given by the following equations. So dc by dt to k1 Ca minus k2. There may mention that the time at which the concentration of B will become a zero. To k1 e raised to the k1 t minus k2. Now integrate Pc k1 t dt minus k2 dt. Right. So Cb to k1 k1 t minus k2 plus constant. Right. So at t is equal to 0, Cb at t is equal to 0, Cb is 0. Right. Minus. So this is condition to calculate this constants. Here 1 0 minus k2 0 plus c. So c is equal to 1. Right. Now so cb equal to minus e raised to the minus k1 into t minus k2 t plus c is equal to 1. Right. So for cb equal to 0, so 1 minus e a to t equal to k2. The option is. I'm moving to the question number 14. An elementary irreversible liquid phase reaction twice A gives B is carried out under the isothermal condition in a 1 meter cube ideal plug flow reactors as shown in figures. The volumetric flow rate of phase A V1 is equal to 10 meter cube per hours and its concentration Ca1 to kilomole per meter cube. For a recycle ratio R is equal to 0, the conversion of A at a location 2 with respect to the phase speed location 1 is 50%. For the R tends to the infinity, the corresponding conversion of A. So here R is for the R0, the conversion given. So R tends to the infinity. So what will the convergence? That's we have to calculate. So for R equal to 0, PFR. This is the recycle ratio. This is second order reactions, Mr. The performance equation of R equal tends to the infinitive CSTR. Right. The performance equation for the second order reaction and PFR for a PFR K tau C naught equal to XA 1 minus XA. So XA given 0.5, right? And CA naught means CA1 given 2 kilomole per meter cube and tau is equal to V by V naught. So 1 by 10 equal to 0.1 hour, right? So put this value in these equations. So K tau say not equal to 1, right? So for r tends to the infinity, the performance equation for the CSTR K tau say not equal to xa 1 minus xa. So this is the performance equation for CSTR or second order reactions. So here K in tau into C not equal to the 1. So put this in this equation. So 1 equal to xa 1 minus xa. So solve this expression. So you will get xa square minus 3xa plus 1 equal to 0. Right. Now to solve these equations, xa equal to plus minus 3 square 4 1 1 into twice. To solve these equations, a is equal to minus b plus minus c square minus 4ac divided by twice a. Right. So xa is equal to 0.3819, means 38.19%, and r tends to the infinity. So I covered all the questions based on the 7 chapters: design, reactor design, perform multiple reactions. So thank you all. We will meet on next Friday on next chapters.